Recording on. And let me start my doc cam. All right, here we go. All right, so section 6, we're getting into exponential functions. So today is going to be based around more of the theory. We'll be just exploring the actual exponential function itself, talking about what it does and how to identify it, that sort of thing. Tomorrow is going to be based more around example problems, similar to what we did with section 5, where I take some day to talk theory, and then the next day I'll talk about examples and actually performing the questions and that sort of thing. Okay, so a couple of main points to understand of this. First off, we're dealing with functions. As soon as you ever see this in an algebra textbook where it talks about functions, you know we're going to be dealing with graphs. Okay, and the other thing I want to remind you about is that when it comes to algebra-based questions, function-based questions, there are kind of 3 families of questions that you'll receive. And you're going to see each of those within this section. Okay, the first family is evaluating. Okay, being given a function and being given some variable's value, it'll probably be x in this case, x equals some number. Plug it into the function, see what pops out the other side. That's basically the process of creating coordinate points. Okay, so if I tell you x is 7, doing the order of operations over here to get what you need to find out what y equals when x equals 7. Okay, that's the process of evaluating. It's kind of the process of creating an xy table as well, but in this single instance. Okay, along those lines, just to kind of prepare you for the most common mistake with these kinds of problems, the most common mistake, people try and multiply a and b, whatever they are. They try and multiply those together first. According to order of operations, I have to deal with the exponent first, just to remind you guys. Exponent comes before multiplication in PEMDAS. So in this equation, if I was given something to evaluate, I'd make sure I'd be doing this base to that exponent first, and then whatever that result was, then I'd multiply it by a after the fact. Okay, so just be aware of that. You will be asked to do that several times in this assignment. Okay, so the first family of algebra questions involves evaluating, taking some number, plugging it in, seeing what pops out the other side, the process of making coordinate points. Okay, the second family involves, here's a function, graph it. Okay, basically, here's some equation, what will it look like visually? Okay, for exponential functions, I have it here in the margin. Exponential functions will generally look like this. Okay, for my students that had me last year, you heard me describe this as a boomerang or a banana. Basically, you're going to get this curve. All right. Now, this curve can be pointed any which number of ways, as you can kind of see here are different versions right here. But you're going to get that general shape. Okay, and so exponential functions will have a very distinctive look to them. Just like the other functions that we've dealt with in Unit 1. In Section 1, we dealt with absolute value functions, which had that V shape, whether it was a happy face V or a sad face V. Okay, piecewise functions in Section 2 had kind of like broken pieces of functions scattered across a coordinate grid. Again, very distinctive. Exponential functions, like we're talking about in this section, will have this curved shape. And the reason why they curve like this is because exponential functions will accelerate. Okay, that tends to be the key term there. That is that they accelerate, kind of like the spread of a disease. Okay, if I'm sick and I get 2 more people sick, and each of those people got 2 more people sick, and that's how it spreads, it's multiplying each new level by 2. And so what you end up with is this very fast growth, and that the more people getting sick are spreading it faster and faster and faster, and that's where we get that curve to an exponential function. Okay, same thing goes for decay. Like as it goes down, it's going to continue to get more and more low in its values. Okay. So anyway, the first family is evaluation, plugging something in, seeing what pops out the other side. Second family is like, all right, now here's a function, graph it. And you can use the XY table, basically using evaluating to build that graph to show what it looks like using coordinate points. And then the third family of algebra questions tends to be the flip side of the second one, which is to say, all right, here's a picture, here's a visual, here's a coordinate grid graph. Based on that graph, pull out whatever function represents that. Okay, because these functions and graphs are tied very closely together. And so if I gave you a graph of some exponential function, again, it'd be pretty obvious with the curve that you would see, you would know it would have to fit into some kind of structure like that because they're tied together. Okay, so you can expect all those types of questions in this section whenever they throw around this term function. Those tends to be the basis of all algebra questions. Okay, so let's explore this function, this exponential function. The most basic version of it is this y equals a times b to the x. Okay, like any functions, we see this y and x combination here. Just like in a linear function, y equals mx plus b, y and x are going to stay y and x. They're considered what we call variables. Okay, essentially, in this function, in this graph, y and x represent coordinate points, all the possible coordinate points of anything that's on the visual graph. Okay, so y and x are variables because they can represent anything as long as it's on that visual graph anywhere on the coordinate grid. Okay, a and b in this case are what we call constants. Okay, kind of like in a linear function, y equals mx plus b, y and x would stay y and x, and then m for slope and b for y-intercept in that case would be some numbers. They would kind of tell you where on the coordinate grid this line went. So for an exponential function, it's similar. A and b are our constants in this case, and so here's what they each stand for. A is going to be some starting amount. Okay, and that will make more sense as we get into some of the example problems, mostly tomorrow. But to kind of use an example right here, if I'm putting money in a bank account and it's growing exponentially with interest, okay, the starting amount would be like the initial amount I put in the bank to deposit. So if I put $100 in the bank and it was growing with interest, the $100 would be my starting amount. On the flip side of that coin, for decay, if I was talking about carbon dating some fossil where I have some bone that I know when it was like it was still a living dinosaur or something, it would have so much carbon, maybe 1,000 grams of carbon, and that now this fossil only has like so many grams left over, and I can use that exponential curve to date how old that fossil is. That whatever it started with, in that case, the 1,000 grams of carbon I know that bone would have had, that would be, again, some starting amount. Okay, and again, we'll get more into specifics on that when I work through examples tomorrow. But A will represent that starting amount. Graphically, for us, within just this form right here, A also represents a y-intercept, okay? Because it's a starting amount. It's when, all right, well, if I'm starting at 0, what's my starting value? That's what it means by starting amount. Initial amount, starting amount, whatever you have. B, the base of my exponent, is actually going to be the most important feature of this entire function. This will be the one that ends up doing most of the heavy lifting. Kind of like with a linear function, slope was kind of the main thing that made it a line. It was that constant rate of change. B is that for an exponential function. This is going to be our constant multiplier. This is basically how it's changing from value to value. So in that example I gave earlier about like if I got sick and I got 2 more people sick and each of them got 2 more people sick, okay, my constant multiplier would be like me going to 2, that's multiplying my sickness by 2. 2 more people have. Each of them got 2 more people sick. Now I multiplied those 2 people by an additional 2. Now 4 more new people are sick. Okay, and then, now you see how that's growing with that multiplication, that constant multiplier. Okay, and this again will be the most important feature of the exponential function. Okay, so I have A, some starting amount. B is what I'm multiplying it by to figure out how it's growing or decaying. Y and X just represent those coordinate options, not options, coordinate pairs on the visual graph of whatever this looks like. Okay, all right. So now let's talk about 2 categories of exponential functions: growth versus decay. This is kind of the equivalent from a linear function of the positive slope versus a negative slope. And they're actually read very much the same way. Kind of like if I read like a book from left to right, okay? If it's going up, it's increasing. So from a linear perspective, that'd be a positive slope. From an exponential perspective, that would be growth, right? If I'm reading left to right like a book and it's going down, from a linear perspective, that'd be a negative slope. From an exponential perspective, that'd be decay, okay? And we'll be able to read both of those in a graph a little bit later. But exponential growth and decay. Your first several questions in this assignment will ask you a very basic question. It's going to give you a function, like each of these examples, right? They'll give you some functions, and they'll simply ask, does this function represent growth or decay? And then they'll ask you about the rate or how much it's growing or decaying. And I'll talk about both of these things. Those tend to be like the main points of exponential functions, okay? But how to identify growth versus decay? It's actually really simple. It's barely math. It's just looking at a number, okay? And we're looking, again, at that most important feature of an exponential function, the base of the exponent, b in this case, okay? So when I look at an exponential function, it's going to fit this structure. So here are a couple of examples of exponential functions. So in either case, the base of the exponent will almost always be in parentheses. Almost always, not always, but almost always. But the base of the exponent is going to be the thing beneath the x. The x is going to be, this is the whole reason why it's an exponential function, is because x is in the exponent spot. But the base of that exponent is going to give me almost all the information I need. And simply put, the way I know it's growth is if b is bigger than 1. It could be only a little bit bigger than 1. It could be massively bigger than 1. It doesn't matter. Anything bigger than 1 is exponential growth in this case. All right? And here's why. Again, going back to what it is, b, the base of the exponent, represents a constant multiplier. Well, let's think about that. If I have some starting amount, right? Like, I don't know, 1,000 of something. Let's call it dollars, right? If I have $1,000, right? And my constant multiplier is 1, right? $1,000 times 1 doesn't do anything. It still stays $1,000. That's what we would call a constant function, okay? It would just always stay the same. So even if my multiplier was only ever so slightly bigger than 1, like maybe 1.01, it's a little bit bigger than 1, and so even that number times 1,000 is going to make that 1,000 a little bit bigger. And if it was a lot bigger than 1, like 500, 1,000 times 500 will get a lot bigger. But in either case, what happens is anytime that base of the exponent, that constant multiplier, is bigger than 1, and this is only a little bit bigger than 1, that's 1.83, it's still going to get bigger. Okay? If I were to take 1,000 and multiply it by 1.83, I would get 1,830. It got bigger. That represents growth. Okay, and that's a simple thing to identify. Again, it's barely math. You're just looking at a number. Is it bigger than 1? Yep, that's growth. Okay. Flip side of that coin. Now, what about decay? Basically, it's less than 1. Again, if it's multiplied by 1, nothing changes, and it's not growth or decay. It's just constant, right? But if it's less than 1, like here in this example, it's 0.67. That's the base of my exponent, the thing beneath the x. It's less than 1. And for the record, you're not going to see anything negative right here. They're not going to do that to you. That would be what we call an alternating sequence, and you're not going to deal with that. But in any case, it'll be some number between 0 and 1. So you're going to end up with some decimal or some fraction that's between 0 and 1. You're not going to get anything that equals 0, because 0 to any power is just going to stay 0. Okay? Actually, the one exception is 0 to the 0 power. We're not going to do that. Anyway, here, 0.67. It's less than 1. Quite obviously, just looking at it. It's less than 1. Okay? It's bigger than 0, but it's less than 1. That's the important part. That means it's decaying. So again, if I started with 1,000 of something, we'll call that $1,000, and I multiply it by 0.67, it's going to get smaller. Okay? In fact, if I were to multiply 1,000 by 0.67, I'd get 670. The 1,000 obviously became smaller. That's what we would call decay. Okay? So just the number, whatever number exists here at the base of the exponent, that's going to tell me whether it's growth or decay. Bigger than 1, growth. Smaller than 1, decay. All right, so the second feature I want to talk about is rate of growth or decay. Okay, rate of growth and decay is a very, very important feature. And almost always what you hear in the real world is you talk about rates of growth and decay in terms of percentages. This virus is spreading at a rate of 37%. Okay, my bank account is growing by 8%. This carbon is decaying at a rate of 1.7%. Okay, percents tend to be the most common used phrase there. And because of that, one of the things they're going to be asked is, what is the rate of growth or decay? So once you identify whether it's growing or decaying, they're going to ask you how fast or how slow it's growing or decaying. That's what they mean by rate. And they're going to want it in percentage form. Okay? And so we're going to actually talk about the most common piece of math that everyone in here is going to ever use without fail, regardless of what you do in your life. The most common thing you will do mathematically is percentages and decimals. That's just going to be the most common thing that you do in your lifetime. Everyone's going to deal with percentages, whether it's tipping someone at a restaurant or figuring out your budget or taxes, the whole 9 yards. Percentages are going to be something that you're going to have to deal with the rest of your life. So how is that applied here? So first off, you're going to see these two formulas. For the record, when the textbook uses these are no different than my original a times b to the x. The only thing that's changed, so to speak, is this b. They're kind of splitting it up to 1 plus r or 1 minus r. Okay, don't get caught up on that. All right, don't feel like you have to memorize those formulas. There's actually a very simple process to pull out like what percent is changing here. Okay, so let's go back to this example. Here in this example, I'm given this exponential function. Again, it's exponential because I have x in the exponent, right? I can see that it's growth because the base of the exponent, 1.83, is bigger than 1. Well, great. I know it's growing. Well, how fast is it growing? That's what they want to know with rate of growth or decay. So how do I find rate of growth? And that's what's here in this margin right here. Basically, it's this. Take the base of the exponent, subtract 1. 1.83 minus 1. That's 0.83. This is basically the above and beyond extra stuff of how it's growing. Okay, whether or not it's a massive number or a small decimal like this, subtract 1. Okay, and that will tell you how much above and beyond. Because the reason why we're subtracting 1, that 1 represents, if it was just 1, that's just whatever starting amount I have that's staying exactly the same. In this case, that 0.83 extra is how much it's growing. Okay, and we'll do that with decaying next. But in this case, the 0.83 extra, so I take that base of the exponent, subtract 1. In this case, I got 0.83. So I have some decimal. So what do I do with that? This is the number I'm going to convert into a percentage. So how do I convert a decimal into percentage? Move the decimal to the right 2 spaces. 0.83 becomes 83%. If I had 0.57, that'd be 57%. 0.16, that's 16%. If I had 0.02, that's 2%. Okay? So be careful with that. The process is the same every time. Just move the decimal twice. If I had 5.47, that would be 547%. Okay? So the conversion is really quick. Just get used to it because you're going to be doing it quite a few times in this section particularly. So again, I would subtract 1. That tells me how much extra is being applied here, particularly for growth. Converting it to a percentage, I would move the decimal twice. In this case, I would get 83% growth. All right, well, let's look at that from a decay standpoint now. So again, I can tell it's an exponential function because x is in the exponent spot. Right? My base of the exponent is the most important number here. That tells me whether it's growth or decay. It's less than 1. This is decaying. And my process is going to be exactly the same because now they're like, okay, is it growth or decay? This one's decay. It's less than 1. All right, now how fast is it decaying? What is the rate of decay? I go through the same process. Subtract 1. For this one, you're going to want to use a calculator. Okay, so in this case, when I say 0.67 minus 1, I'm going to get negative 0.33. I left the negative off there in my result right here, but if I subtract 1, I would get negative 0.33. The negative for us just means it's decaying. Okay, so from a percentage standpoint, I'm just going to use the actual number, not the negative sign or whatever. But if I subtract 1, that tells me it's negative 0.33. This tells me how much below 1 it's going to be. Again, if I multiply by 1, that's just the original thing. However much it's below 1 tells me how fast it's decaying, how fast it's shrinking. In this case, it's 30.33 less than 1. That's how fast it's decaying. And again, just like before, I would move the decimal two spaces, and that would be a 33% decay. So walking through that again, I would take my base of the exponent, subtract 1. In this case, it would be a negative 0.33. Again, all the negative means is that's decaying. Okay, so I can kind of ignore that. But that 0.33, I move the decimal twice, 33% decay. It's decaying at a rate of 33%. Okay. And kind of lastly here, just seeing visually what that would look like. A growth function, again, reading left to right like a book, is going to be increasing. A decay function, reading left to right like a book, is going to be decreasing. It's going to get smaller. Okay. So that's where I'm going to go ahead and stop today. Let me go ahead and stop recording.